One of the next topics we're going to start to talk about is known as acceleration. You've probably heard the term before. You may not entirely understand its meaning within physics. But if you think about it in terms of what you've probably experienced, it'll probably start to fall together as we discuss this. I think one of the best examples to use is the example we use in class regarding a person who's running around a circular track. We all know from our discussions about velocity that the average velocity as this runner completes one lap would be zero. And that has to do with the fact that his overall displacement is zero as he began and ended the race where he started. I get a lot of questions, and they're valid questions, as to how that makes any sense. Because if he ran an entire lap, how could we say that his average velocity is zero? Well, we know now that it's because his total displacement is zero, but it's important to start to realize that that's just an average. That is the average velocity. If we were to add up all of his velocities throughout the entire duration of the race, that's where we come up with that zero term. But I think most people realize that, let's say the official shoots the gun and the race starts. I think most of us realize that he's not going to have a zero velocity at any particular given point throughout this track. As he's running this way, if we just assume an orientation of northeast, south, and west as shown, at this point, as he runs this way, it would be safe to assume he has some kind of velocity due west. As he rounds the corner, he'd have some kind of velocity due south, because as he comes through here, he'd be running south. As he runs along this bottom section, he would be some kind of velocity due east, this section due north, and then he'd be due west as he returns to the start. Now, as he goes through the curves, here he'd be going at this specific point, he'd be running in a southwest direction. As he continued and ran here, he'd be running in a southeast direction, and so on and so forth. Hopefully, you start to see that not only will the magnitude of his velocity change, while he starts at zero, he may be running 5 meters per second here. He may speed up to 7 meters per second. He may slow down to 3 meters per second. I would imagine that near the end of the race, he'd probably be a little bit slower. Unless he's in incredible shape, he's probably going to have expended most of his energy through this section. But it's important to realize that at each individual section, at any given point, his velocity is not necessarily going to be zero. And that with that comes an important term. We haven't really spoken about this. I apologize. Yeah, it's known as instantaneous velocity. We have spoken about, we've spoken about average velocity to this point, but instantaneous velocity has to do, let me just make sure I spell it correctly, instantaneous velocity, that is the velocity at any given instant. So while the average velocity through this entire lap is zero, well, if this runner begins to run, what is his instant velocity at this specific point right now? What is his velocity at this instant here? What is his velocity at this instant, and so on and so forth. So instantaneous velocity is the actual velocity you're going at any individual point that you're interested in looking at. If we were to average all of these instantaneous velocities for one lap, that's where we would get an average velocity of zero. So hopefully you're starting to see that the velocity at any given moment is a specific value, whereas the average, much like a class average on a group of tests, is just kind of the collective average of the whole. So think of this instantaneous velocity, the velocity at any individual point, as like an individual test taken by one student in a class. The average velocity, what is the total average of all these instantaneous velocities? Much like in a classroom, what is the average of all these individual tests? And this is where we really get to this idea of acceleration. Most of you probably think of acceleration maybe in your car, maybe if you're an athlete, when at the beginning of a race. What we want to look at here is acceleration is essentially a more basic definition is just when you start to pick up some speed, and within physics we like to say velocity. So as you're gaining or losing velocity, if there's any kind of change in velocity, you are either accelerating or decelerating, depending on whether you are gaining or losing velocity. So to put it into terms, excuse me, of what we already know, acceleration is represented by a small letter a, and as mentioned, it's just the change in velocity over a given amount of time. There we go. Given a velocity, change of velocity over a given amount of time, you'll notice that it's somewhat similar to our velocity equation, except instead of dealing with displacement, we're much more concerned with what's our change in velocity. So velocity, how much more ground is being displaced, how much more ground is being covered. Well, acceleration wants to know how much speed is being gained or lost over a given amount of time. So this is your basic equation. This is definitely the equation you should have written down somewhere. We're going to be using this equation a lot moving forward. But to break it down instead of a mathematical equation, acceleration is basically the change in your velocity over a given amount of time. Are you gaining velocity or are you losing velocity over a given amount of time? And to give you some examples, we'll take a look at this runner right here. Actually, let me go back one. Let's take a look here. So we have two examples, two viewpoints of the same event. We have a car that's at rest. 3, 2, 1. We're getting the countdown. As soon as the gun is fired or this race begins, this car is off. So the important thing to realize, in this case right here, we have an instantaneous velocity. Bear with me 1 second. We have an instantaneous velocity right here. We'll call it v with a little 0 to show you your initial. Your initial velocity is 0. You're not actually moving. If I give some numbers, let's say that the velocity at this point, we'll say final velocity, I guess. So the final velocity here, let's say, is 20 meters per second. Well, if we assume that 5 seconds has elapsed, we should be able to hopefully take a look at the acceleration of this car. We know that acceleration from our previous slide is the change in velocity over change in time. So we just have to take a look and see what our change in velocity is. Well, change is always final minus initial. So it's going to be our change in velocity over time. Our change in velocity in this case is our final minus our initial divided by our time, how much time has elapsed. So we have 5 seconds. This should reduce to 20 over 5. And this, of course, is 20 meters per second. This is 5 seconds. We wind up with 4. And this becomes an interesting unit. The way we actually say this is technically meters per second, which is much easier to say as 4 meters per second squared. So it's important to realize this is your equation for acceleration, and it would probably be a good thing to note right now that your units for acceleration are going to be meters per second squared. If we want to take a look at another example, let's take a look at this runner here, and let's change it up a little bit. Let's say that this runner, from the start of the race to the end of the race, well, let's say this runner accelerated at a rate of, I'll say 3 meters per second squared. So the acceleration of this runner is 3 meters per second squared. If he accelerated at this rate for, let's say, 2 seconds, then the question would be, what was his final velocity? Hopefully you realize that we're not talking about average. We have his velocity when he begins. If he's standing still, his initial velocity is 0. We don't know what his final velocity is. That's what we're looking for. If we use our acceleration equation, however, we know that acceleration is equal to your change in velocity over your time. And we know that the change is equal to the final velocity minus the initial divided by the amount of time, which in this case is 2 seconds. We also know that our acceleration is given, so we know that this is going to have to equal 3 meters per second squared. So if we want to go ahead and solve this out, we'll multiply both sides by 2 in order to eliminate the denominator. So what we'll wind up with is your final velocity minus 0 equals 6. We obviously know your final velocity minus 0 is just your final velocity. So you wind up with 6, and don't forget the units, meters per second squared. This unit confuses some people, but all this means is you gain 6 meters per second of velocity per second of time elapsed. And we'll talk a little bit more about this in class, but as long as you can understand what your acceleration equation is, and for now you know what your units are, you should be on the right path.